So, hello, everybody. It's the great privilege and honor for our community at SDU to welcome Professor Stefan Hell, who is the Nobel Prize, as you know, laureate from 2014. And he will, of course, present his research, and I'm not going to interfere with that. But I would like to say a few words, maybe like in a way of introduction to the field of microscopy in general and to the issue of super resolution, so that you would be able to really guess, to gauge the importance of this issue. So the story about microscopy actually goes way back. It's all started a long time ago. So even from this time, that has been so nicely pictured by Gary Larson, my famous favorite cartoonist from United States. And then it was been progressing to the microscopes, more or less, that have been established at around 1620 or 30, that started to look exactly the way like conventional microscopes look today. So with the resolution that was achieved between hundreds and several hundreds, it was clear that it's a very powerful instrument, but it was not clear how good resolution can actually be. And here we should switch on or move on to the Ernst Abbe, who is really put a great deal of efforts into figuring out what are the limits in the resolution when you are using conventional microscope. And it's actually very simple reasoning. So one has to consider the object, for example, like diffraction grating. And when you send the light on the diffraction grating, then you have the transmitted light and the diffracted light. And this angle of diffraction is related to periodicity. So there is a very simple formula here. So you can see that the smaller periodicity, the smaller features you would like to see, the larger would be the angle of diffraction. So now let's try to see if you are using this in imaging. So here you have the object, like the grating, and the lens. So if the periodicity is large and the angle is small, so that diffraction is not moving light too far away, then the lens, imaging lens, would recombine these orders, and by means of interference, you will get an image. So this is what you will see in the case of coarse grating with large period. When you go to the fine grating, then the angle would become much larger because the periodicity is smaller, and it can happen that the diffracted beams are coming, not passing through the imaging pupil. And therefore, in the image, you will see just uniformly illuminated screen. So there is no image whatsoever. And that brings us to the resolution limit as determined by or derived by Ernst Abbe. And this is actually carved in stone in the Jena. It's a city in Germany where he made his research and investigations of optical resolving power of microscopes, where you can see that the resolution is limited to the wavelength, refractive index, and here we have this alpha, that is aperture, gives you the angle of subtension. So you can see that if you put here 90 degrees, then it's lambda over 2, right? You can view resolution from another point, and that is about making an image from the point source. Then because of the diffraction, you're going to have, if you have two spots here, even if they're infinitely small, then you'll have a spreaded size. It's called Airy pattern. And So it's called Taylor pattern because they recalculated it. And if the objects would move together, then they would start to overlap, and suddenly you no longer be able of resolving them. So actually, the contribution of Lord Rayleigh, which is also has a name on the resolution limit, is that he said, okay, we can still resolve these two images if the maximum of one spot would be exactly at the minimum of the first area ring. And that gives another formula for the resolution, but you can see that this is close to 1/2, and this would be again, for the numerical aperture 1, it would be λ/2. So no matter how you look, the resolution is limited to the half of the light wavelength. Now we come to the beating the resolution limit, and to the person who really made a great impact on the development of all super resolution techniques, Hatchie or Edward Hutchison Tunge, is actually not scientist, but more like a teacher in gymnasium. And this is his paper that was published in 1928, and where the whole foundation of the super resolving microscope has been put, and I really admire his modesty, because he writes, yet a method offers itself. You know, not like I figure it out how to do that, but the method offers itself. I wish I would be that lucky. And then he knew that he did something good, but he was not sure that it should be even published. So he contacted a distinguished physicist, and that was Albert Einstein. And this is the letter from Einstein, who recommended that you should publish this paper. And this is what he did. So the modern realization of Tunge idea, it's something like that. So there is a light coming through the tapered fiber coated with the metal, so that it can escape only through the small aperture. And now you imagine here you have an object, and of course the object can be either blocking light coming from this small aperture or not. And by scanning this fiber, you will get the image that would be essentially limited only by the distance to the distance between probe and the sample, and by the size of the aperture. You can say that it's in a generic configuration, something like that. So it doesn't have to be aperture, it can be a scatterer. But the point is that it should be small distance, it should be small size of the probe, and then scanning as a means of retrieving the image. And in that case, as I said, the resolution is determined by the distance to a sample and not and the probe size, but not by the light wavelengths. Light wavelengths in this case absolutely irrelevant. Actually, this is the techniques that most of you know from the medical science, because everybody knows about stethoscope. And if you think about the way it operates, the acoustic wavelengths of the frequencies associated with heartbeats, they're around tens of meters, right? But the accuracy provided by the stethoscope, I mean, you know that a doctor would always find your heart on the right side, right? Not on the wrong side of your chest. So it's only 1 centimeter. It's 1 centimeter, so it's a huge difference in sizes. But essentially, this is the near-field, acoustic near-field probe, which scans close to the sample. And then the signal picked up by this tiny probe, and then your ears, they serve as the detectors. And actually, the first experimental paper that really demonstrated this principle, which you can say it's a principle proposed by Tunge, it was a paper from IBM Zurich Research Laboratory, famous at that time because it was the invention of AFM, atomic force microscope, or even earlier scanning tunneling microscope. And this is the device that's essentially, well, it's clear, like what I showed you, the fiber and going through the, in that case, it was just rod and then illuminated and picked up and detected in the far field. And the person who was behind this research, Dieter Pohl, that he is also really introduced this nice explanation and analogy with optical stethoscopy. Okay, well, I hope I gave you the understanding, or at least a glimpse of the enormous efforts that have been paid to the issue of the resolution over the years. And I don't want to detain you from listening to our guest of honor, Stefan Hell. And I would really recommend to read this Nobel lecture, Nanoscopy with Focused Light, because there it's the proper introduction, much better than I made, is given in the proper description of the principle. And I still have to say a few words about this principle. Maybe it would give you forewarning of what you're going to hear. But the idea is also to show why this technique really stays away from what I have described. And it's still super resolution. So here the idea is to use 2 laser beams and one which is excitation that excites all the molecules. And the one that causes the stimulated emission is doughnut beam that actually brings all the excited atom molecules down to the ground state in this area, so that the only molecules that are in the very center, they are still excited, and they provide you the light that you image. And the point is that the dependence of fluorescence ability on the intensity of illumination with this stimulated emission is sharply nonlinear. So you can put this threshold very close to 0, and that means that you can have only really few molecules from the very small spot that would give you the image. So that's the idea. And as we all know, it works. And the paper was published in '94, and I'm actually happy to say that you can see there were not so many citations at the beginning, but at least I remember very well the impression that I got when I read this paper in Optics Letters, because I was already in near-field microscopy and giving a course to my students. And when I saw this paper, well, there I was just astonished. I would say, wow, that is really an amazing technique and so unexpectedly turning around the whole issue of super resolution. But now how to relate these two fields is that this is what was brought with Stefan pioneering work, is that once you have nonlinear light-matter interactions, then you are no longer bound by resolution limit. So the resolution limit and Abbe formula, it's still there, but it's for linear optics, for linear responses. So nothing's going to change that. But once you are smart enough to employ nonlinear interactions, there you can go far beyond, even without using probes, as so nicely demonstrated by Stefan. So, and well, it was a good story that came to Nobel Prize to Stefan. And I would just like to say that there are key components. First of all, that was a pioneering concept, just in case that somebody would think it's so easy to get a Nobel Prize. So first, it was a pioneering concept. It was really out of jumping, like out of nowhere. Then, after actually great many trials and experimental hard work, I know from the Stefan co-workers that it was really difficult to make a first demonstration. Several years later, it was demonstrated. But even not, that was not enough. Then the instrument was developed. And with developing the instrument, Stefan's development or invention really brought enormous impact on imaging and life sciences. And with that, I would really now like to welcome Stefan to start his lecture, and I hope I did not use too much time. So please.
Thank you very much, Sergey, for introducing the topic so nicely and for introducing me. Actually, it saves a lot of my time. It doesn't consume up my time, on the contrary, because I don't have to speak about those things that you have explained so nicely already, namely STED microscopy. So thanks for having me here. It has been a very, very nice morning today, seeing what has been set up here actually in terms of microscopy capability. I'm very impressed. And so it's hard for me to tell you much more than you have already, but I'm trying to show you, so to speak, the cutting edge of it, at least from my perspective. That's why I called it the cutting edge of super-resolution fluorescence microscopy. Now, as we've heard actually from Sergey, maybe it's possible to dim down the light a bit so that the images come out a bit more visibly. That throughout the 20th century, the resolution of any, say, light microscope was fundamentally limited by diffraction, which was very much in accordance with what Ernst Abbe and, of course, Lord Rayleigh predicted. And the workhorse, at least in biological microscopy, was confocal microscopy, which provided, I would say, much slightly crispier images and also three-dimensionality, which was very important, but didn't change the resolution issue. So the resolution was still limited to about a fifth of a thousandth of a millimeter, so about 0.2 microns or 200 nanometer. Now, the development of STED microscopy, as Sergey nicely explained, showed that there is, say, viable physics, so to speak, that really gives you higher resolution even in a microscope that uses regular objective lenses, so focused light. And one didn't have to squeeze the light through tiny holes, as suggested much early on. So this was a kind of surprise at that time, and that led to a resolution increase roughly by a factor of 10. So from about 200 nanometers to about 20 nanometers at most. So there are some exceptions where you can get better, but 20 nanometer is already the edge of the capability of STED microscopy. And of course, since this was kind of surprising, as we've heard, this has led to a share of the Nobel Prize of 2014 in chemistry. And what you see actually is here a sketch of the STED microscopy operational principles. So I have a beam that is limited by diffraction that turns molecules on, excites them, so to speak. Then you have a beam that turns them off, as Sergey has explained. And then, of course, those molecules that are still allowed to emit, they are confined to a much smaller region than previously, so there are fewer molecules that are capable of emitting. And because they have to be here in the center of the donut beam, whose position is always perfectly controlled and known, it's possible to get a high spatial resolution because you can separate those molecules from those that are slightly further away. And that's why this concept, of course, was very, very successful. Now, the first experimental demonstration, actually, of STED microscopy was around 99, 2000. And a couple of years later, 2006, Eric Betzig, a gentleman over here, presented a microscopy concept that relied on the same principle for separation as STED microscopy, namely these turning molecules on and off. But it was implemented in a different way, in a fundamentally different way, which was turning on and off molecules on a single molecule basis, such as only one molecule, say, emitting at a time and the rest is off. So the new thing here was not the principle of separation, it was still on-off. As a matter of fact, not even the molecular mechanism by which this on-off was done, namely cis-trans isomerization or photoactivation, was new in the field. What was new was the fact that molecules were detected individually, and the person who actually saw the first molecule individually on a single molecule basis was this gentleman, W.E. Myrna, at that time at IBM in California. And so that's why I had the honor of sharing the prize with these two gentlemen. So the principle of separation is the same, and there's something else that these microscopes, PalmStorm, or as it is called, and STED have in common. In theory, they can attain a spatial resolution that really goes down to the size of a molecule. And the size of a molecule is 1 nanometer. I should say the size of a fluorescent molecule, in principle. But in practice, at the time, the Nobel Prize was given, none of them, neither Palm nor STED could get a spatial resolution that was substantially better than 20 nanometers. So this was a kind of practical limit, although conceptually they could have gone further. So the Nobel Foundation actually, maybe it's coincidence, maybe not, actually put it quite correctly. The microscopes crossed the threshold, but what I'm adding now is, but they did not attain the ultimate limit. And I personally, since I've kind of tied my scientific life to this resolution problem, I was very much interested in getting further. I anticipated that in theory it should be possible to get down to the molecular limit, so why not getting there if it's theoretically possible, and what are the obstacles, and maybe it's possible to overcome the obstacles. Now, I'm going to speak actually just about that, how to get down to the fundamental limit, which is about the size of the fluorescent molecule. It's not possible to get beyond that, in terms of resolution at least. And I'm going to show you why this is now routinely possible, not only in my lab, but also here at your place, as I've witnessed today. And I'm going to show you the principles behind this, you may call it a second big step in the super resolution fluorescence microscopy that now allows us to get down to the molecular level. Now, if you really look at the problem from a slightly different viewpoint, you can say that the reason why people thought that it's not possible to go beyond the diffraction barrier or smaller than to the scale smaller than about 200 nanometers in terms of resolution was the fact that it's not possible to focus the light down to further than down to 200 nanometers. And so if you are having molecules that are at this distance here, 11 nanometers, they all will be illuminated at the same time, and hence they will emit light at the same time, and it's not possible to distinguish a signal from these molecules. Therefore, it's not possible to separate them. That's one way of phrasing these things. Now, separating the molecules on a single molecule level is, of course, inherently an advantage if you want to get down to the resolution that is at the size of the molecule. So this on-off principle of separation is extremely powerful. As I said, it's used in STED, it's used in PalmStorm, but in PalmStorm it has the big, so to speak, advantage that PalmStorm inherently deals with single molecules. And if you want to get to molecular resolution, it's of course an advantage to deal with single molecules, because this is the smallest entity that you can distinguish, that you can separate. And so if you implement it on a single molecule level, it means this on-off transition, it means this molecule has to be on, and the rest has to be off. Then you have a chance of telling this apart from the rest, because only this one is emitting, the rest is not. Yeah? And you need to have, of course, a mechanism by which you keep this one on and keep those things off. And then you go to the next. It could be randomly, stochastically, of course, and then you turn this one on and the rest is off, and then you go to the next, and then you go to the next. Then you have a chance of separating these molecules, provided that you know where these molecules are. Because if you don't find where they are, you don't know if it's this one or that one or that one or that one. Could be any of those, yeah, if only one is emitting, and you will never be able to tell which one it is. You have to find out where it is. Now, PalmStorm inherently by its concept does that. They turn on molecules individually and then try to find out in the concept where the molecules are. But as a matter of fact, as I said, at the time of development of 2014, the time the prize was given, the precision with which you could find out where the molecule actually is was not good enough. It was just about 20 nanometers. So in this cartoon, you couldn't know whether it's this molecule that is emitting, or that molecule, or that molecule, or that molecule, because it could have been any of those 4 molecules. And so the precision was not good enough in a standard pulse situation. This is why the molecules arranged in this cartoon-like fashion here, as it is shown here in this cartoon, are not separated here on the right-hand side. Simply because the precision with which you can determine the position of a molecule simply was not good enough. So here, if it's this one that is emitting, it could have been also that one, maybe that one, and also that one. And so you don't know. That's why this image here is blurred. So the localization precision is insufficient in palm storm, and this is why so a standard palm storm microscope, although it worked with individual molecules, when it comes to separation, couldn't get sharper images. And now I'm explaining why this, say, localization precision is so limited in a standard palm storm situation. Now, typically, the localization of individual fluorescent molecule is done in the following way, and this is shown here in this cartoon. Usually, one has, say, a standard wide field microscope, so-called epifluorescence microscope, which has a lens here. And then, of course, nowadays lasers are used for illumination. You have a laser, and that laser illuminates here the focal plane. So this is why I'm showing here, this is the focal plane of the microscope. It's a wide field system, and it's all green light. Green light means light that excites molecules to emit yellow light, yeah? And so this is a single molecule for the moment, yeah, that emits light, yeah? There's only one here in the focal plane, and we want to find out where it is. So where is it here within the plane? Could be here, could be here, could be there. We want to find out the position of these molecules with the highest possible precision. Now, what people usually did, and still do the very day, in order to find out the position of the molecule, and they've been doing this for decades, actually. So the concept of localizing this way goes back to the 30s. Actually, the first account that I know of is Werner Heisenberg in his book written in 1930. Actually, he mentioned this already. But anyway, so what they usually do is they collect the fluorescence, so the yellow light or orange light here, then project it onto a camera. Camera consists of many pixels, as you know, like a CCD camera or whatever. And then, of course, what will happen, since the molecule is a point source, it will produce, of course, light that is diffracted, of course. That is diffracted here by the optical system. And what we'll get here on the camera, so to speak, on the screen, is a blob of light that looks like the picture that has been shown by Sergei and described by Lord Rayleigh. So it will be a diffracted spot that has its finite extent, and the extent has nothing to do with the extent of the molecule, because that's point-like, 1 nanometer in size. This will be rather broad, and in terms of width, here in the focal plane, it will be about 200-300 nanometers in diameter. Now, that's not a problem. That's what people usually do. They say, oh, no problem. We can still find out where the molecule is, because we know that the position of the maximum of this fluorescence spot here must coincide in space with the position of the molecule. So although this is actually quite blurred, the maximum still must correlate by simple geometrical optics with the position of the molecule. At least that's the narrative. And then, of course, if you calculate the position of that maximum, and that can be done by making a fit or so, you will find out where the molecule is. Now, if you do that fit, you will instantly find out that the precision with which you find out the position of that molecule scales inversely with the square root of the number of detected fluorescent photons. So the molecule emits photons, say n in total, say it could be 5,000 or 10,000 or so, and then the precision that you will get scales inversely with the square root of the number of detected photons. So the more fluorescence you get on a camera, the more precise you will be, but watch out, it scales only with the square root of the number of the detected photons. And this is the way people localize molecules in palm storm to produce images, or localize molecules when they track molecules in the focal plane or in a bacterium or whatever. And so this principle of localizing molecules heavily relies, or fundamentally relies, on the maximization of fluorescent photons. So the more I have, the more precise I will be. And that is the problem of it. And this was the real reason why, or one of the reasons why it was not possible to get below 20 nanometers in precision, because, you know, I mean, fluorescent molecules, they are not just ideal, they bleach sometimes. So they go off, they go into a dark state. Then, of course, if you need many photons, you have to wait, because you need to wait until you have collected all your photons that you need. So if you need 10,000, you have to wait for a long time. If you need 100,000, you have to wait 10 times longer. That's very clear. So waiting means that you are relatively slow. It takes time till you get a high precision, but that's also a problem, because if the molecule moves, then it has changed its position, and then you can find out where it is. And then there is a more serious problem that is appreciated by physicists or physical chemists. Molecules are actually small, that's true, but still they emit like dipoles. And a dipole, of course, has an orientation in space, and if that rotates, it also shifts the pattern around. So the pattern that you've seen actually can be shifted to the side on the screen. And that is a quite substantial effect, especially if the molecule is slightly out of the focal plane. That can easily amount to 20, 30, 40, 50, even 80 nanometers. And that completely spoils this principle that I've been mentioning. So it means that you might calculate the position of the molecule here, but it might be off systematically by 20 nanometers, and you don't know which direction it's off. And so all these problems contribute to the fact that a standard palm storm microscope doesn't get below the 20 nanometers. And that has led to a reasoning that dawned on me quite early, but I decided to look into it in around 2011 or so as a project. And I'm going to argue from a physicist perspective why this is the right way of doing it. You know, if you want to find out a coordinate in space, so if you want to define a coordinate in space with photons are really bad at defining coordinates because there's diffraction, or as Heidelberg would say, well, there is an uncertainty principle, and you don't know where it goes and which direction it flies, and when it flies certain direction, you don't know where it is. Meaning that if you deal with one photon, you could never be more precise than the diffraction barrier of lambda over 2 when it comes to defining a position. So as I indicated, in order to define a position, you would have to so you would have to have more photons, yeah, and so this is and this is very difficult here. But if the photons come from a laser, of course, then it's very easy. But because if photons come from a laser, there is plenty of photons that come from a laser, and then it's very easy to kind of determine a position with very, very high precision. So as a matter of fact, if the photons come from a laser, you can easily define, there's a glitch here in the system. That's why I cannot move the slides. I'm noticing it. I see. Sorry. It asked me to install Java version. That's not what I want. So that's the downside of transferring files. But maybe.
See, is it stuck now?
But I'm not sure it may. Okay, now it moves on. Okay, but doesn't matter. In the end, the message is very clear. With photons from a laser, where you have zillions of photons, you're not limited by the fluorophore. You can easily define a position in space because there's no shortage of photons. So it's always better to use a laser for defining a coordinate rather than use the emission of a fluorophore. So because there is no shortage of photons coming from a laser. And that's the idea behind this MINFLUX concept. And so how would you then use the photons from a laser to find out the position of the molecule if it's all about the molecule? Well, it's very simple, and I'm explaining this to you. So in essence, the idea will be to make a donut-shaped beam, but not for turning off molecules as we do in STED, but for exciting molecules, for making them emit, yeah? We don't want to turn off anything since we have only one molecule here that is in stake. And then, of course, we just want to find out the position of the molecule. And the whole problem boils down to finding out where the position of the molecule is with respect to the position of that coordinate that has been made by the donut beam that has been made by the laser. And so it's very clear that we are using a laser, but it's now shaped as a donut, as you see here. And this donut 0 is very well defined. The position is always very well known because the position is determined here by a beam deflector, like a Galvo or any other device that can steer the donut easily around the focal plane. And then the whole thing boils down to finding out how far the unknown position of the molecule is actually from the known position of the donut 0. So this is, it just boils down to a distance measurement because, as I said, this coordinate is known, but this one is unknown. And then you don't need a camera because it boils down to a brightness detection, because if the molecule is here where there's a lot of intensity, then the molecule will be brighter. If it's just overlapping, if the two are just overlapping, there will be no emission. Why? Because there's no excitation lights, because the donut has a intensity 0, a minimum here at the center, and then there will be no detected photons here at the detector. So we don't use here a camera as it is done in a normal case, but we use just a detector like a confocal detector that measures the number of emitted photons here in, that are emitted by this molecule. And as I said, the position is found out, but just by looking how far actually the molecule is away from the donut 0, and that is actually reflected by the brightness of the detection. So here, of course, there are not many detected photons because the molecule is very close to the donut 0, but still it's not 0 because 0 it's only if the two really coincide in space. And then, of course, the question is, why is this an advantage, localizing molecules like this? Why is this good? Why not still using a camera? And in order to explain this to you, and with my last name being Hell, I felt I have to introduce a demon. And this little demon knows something that we humans don't know. Physicists are aware of Maxwell's demon, so it's kind of something, a creature or not a creature, that knows something that we don't know. And in this particular case, the demon knows where the molecule goes. Let's assume the molecule, or where the molecule is. Let's assume the molecule starts moving. Then the demon would do the following. It would shift the donut around, so by acting on this beam deflector, such that the 0 of that donut perfectly coincides in space with the position of the molecule. And if the two coincide in space, of course, then of course the demon knows exactly where the molecule is, so the demon can perfectly control the position of the molecule. That's very, very clear, so it can really map it, but without requiring any fluorescence emission, because there would be no fluorescence emission here because the donut 0 has a 0 intensity point here, that's clear, and then the molecule doesn't emit. So in other words, you see that it's possible to design a concept that reverts the initial idea of maximizing photons. Here it is minimizing photons. In a way you can say we look for the absence of fluorescence emission rather than for the maximization of fluorescence emission, which of course is a big advantage. And there's another advantage that this concept entails. If you think about it, you will realize that even the wavelength dependence is gone, although this is all done with focused light. So this is just focused light. And to a physicist, this is really weird because you would think that whenever light propagates, anything must scale with the wavelengths. But if you look into the precision, and I'm coming back to that, with which you can locate the molecule, even the dependence on the wavelengths is gone. This is not the case in Palm Storm, it's not the case in STED, but here it's the case. And the hand-waving argument for that is very simple. In the end, what we do is we match 2 points. A molecule is a point and the donut 0 is a point. And if you match 2 points, the wavelength doesn't matter. It could have been green light, red light, blue light, whatever. In the end, the only thing that we care about is the fact that there is a intensity 0. And so the wavelength really doesn't really matter as long as the molecule is excited by the wavelength. Okay, now that has been a demon. Demons do not exist, as we all know, but we can come up with a concept, with a system that works practically, also in your lab, that kind of comes close to this demon situation, or tries to come as close as possible to the demon situation. And in that case, of course, what do? We use a controller here that measures the number of detected photons. So the photons are detected here, counted 5, 10, 100, or whatever. And then the controller kind of guesses where the molecule is, and then depending on the brightness, and then acts on the beam deflector to shift the donut around such that the 0 comes very close to the molecule, ideally overlaps with the molecule. And in this way, of course, you can track the position of the molecule with very high precision, but you need much fewer detected photons, because this concept tries to minimize the number of detected photons by bringing the 0 very close to the position of the molecule. Or I should say, we kind of inject the position of the molecule to a coarsely with the laser beam, and that the fluorescent photons that are produced by the molecule are just used for fine steering, for looking at a small difference between the 0 and the molecule. So the way we put the burden of requiring many photons from the molecule onto the laser, and that's wise because the laser emits light constantly, there's no shortage of photons, and you don't have this problem of say, the molecule going off and moving away, because you need much fewer photons. Okay, so how it is done in practice. So because, as I said, there is no demon that can do that for us, I'm going to show you how it's done in one dimensions. In one dimension, what you would do is, let's assume that there is a molecule here, and you would need to find out where it is. So it could be either here, or anywhere in between the two. So let's assume for the moment it's here, and we don't know that it's here. So what do? We use the doughnut, scan over that region, yeah, and find out where the intensity is minimal. So this is the intensity of the excitation light. So this is the cross-section of the doughnut, so this excitation intensity. And now we scan it across the molecule, and now you see the fluorescence gets a dip here. Fluorescent signal here is minimal, and this must be the position of the molecule. Very clear, because where the intensity here is minimal, this must be the position of the molecule XM. And this way we can find it out. In reality, we don't need to scan that donut as densely as I'm showing here in the view graph across the molecule. Why? Because we know already what this curve would look like, simply because we know already the intensity of the donut here in the focal region. So we know it's the first approximation of parabola, and then it's perfectly enough to measure the fluorescence at the endpoint here, and then jump right to the endpoint there, and 0 and 1, and then extrapolate on the position, because this is a parabola, and simple algebraic inversion in principle gives you the position of the molecule. And here's this algebraic inversion of the position XM, so 7th grade algebra. And then and you get this position in this very simple expression. And this is quite, I would say, quite revealing, although it's very simple as an expression, because it shows there's no wavelengths anymore in this equation, and also the molecular orientation doesn't matter. And this is not the case, as I said, in Palm Storm or in the standard localization. There, the wavelengths matters, the wavelengths of emission matters, and molecular orientation matters a lot. And this is completely gone here. And so the question is, how precise can you be? Because in the end, the proof of the pudding is in the eating, as the English would say. And then so the precision that you get still scales with the square root of the number of detected photons, and the number of detected photons in this case is n0 plus n1, n0 plus n1. But, and that's the new thing, it scales also linearly with the distance L, where we look for the position of the molecule. And that's very good, because that can be made smaller. So if we make that region smaller, of course, then we get a higher precision. So in other words, it means that what we should do is we'd always try to make that region where we look for the molecule smaller, or put it more simply, we should bring the zero as close as possible to the molecule, because the closer we bring the zero to the molecule, the fewer photons we need to get a certain precision, or the more precise we are for a certain number of photons. So the idea, you see, the idea is to bring the zero on average as close as possible to the molecule, because then the precision goes up. And in this way, of course, it's possible to crank up the precision substantially over what you do when you do normal localization in biophysics or in palm storm imaging. In 2 dimensions, it's not enough to have 2 points. It's better to have 3 points, of course, because 3 points define a plane. Even better to have 4. The commercial system, by the way, uses 6 points or 7 points. So it's a matter of flavors and technicalities, how you want to implement it. We did first in our demonstration with 4 points, but it boils down to the same thing. It's always wiser to bring the zero as close as possible to the molecule rather than wait for more photons to be accumulated, as it is done in a normal localization. And that is reflected in the fact that the precision scales down with the region L in which the molecule is located. But for those of you who want to apply this method, of course, they don't care about the rationale and the physics behind it, of course. Why would they? But they may care for one simple rule of thumb. So in practice, at this stage of development, you can save up to 100 times the number of detections. So you can get the same precision with 100 times fewer emitted photons. That means also that if you want to have a certain precision, you can be 100 times faster because you need 100 times fewer photons. So you can either be 10 times more precise, the square root of 100 is 10, or you can be 100 times faster. So both are viable. And that's why we've been able, with this concept called MINFLUX, to separate now molecules that are at this 11 nanometer distance. Yeah? So we could separate them here, but here, as I said, in palm storm, it's not possible. Now they are individually resolvable because the precision with which you could find out each of the molecules, position of each of the molecules was 1 nanometer or slightly below. Again, each of the molecules was turned on and off individually. That's the requirement for separation in all these super resolution fluorescence microscopy methods, but here the precision is much higher. Even 6 nanometers could be resolved at that time, but not with palm storm. And keep in mind, and this is something that Sergei and I, of course, remember those days when everyone really believed that if you do microscopy with a lens, you will never, never, ever get substantially below the diffraction barrier, maybe a factor of 2 or so. But that one day will have a spatial resolution that is truly at a molecular scale. So you're down now to nanometers. That was, I would say, even 10 years back or 12 years back, quite, although it was conceptually thinkable, people would have said, not really. Even I would have said, I'm not sure if that will be possible. Conceptually, yes. But now it's there. It's very, very clearly it's there. Why? Because fewer detections are needed. You can localize faster, less drift, and there's a negligible dependence on the emission dipole orientation. And that all contributes to the fact that this resolution is possible. Then I would like to give you another, for those who have a more physical chemistry background, another insight, which I believe is important to make clear that this is a game changer. If you localize molecules like within a range like this, yeah, in a normal way, you have a square root of a square root dependence on the number of detections. But in this MINFLUX case, yeah, the precision scales exponentially. So basically, with the number of detected photons. So this is why this is a totally different thing. So also in STED, it scales with the square root. Here it scales exponentially. And this is why this is here to stay. It is a new way of finding out the position of the molecule, because searching for the position of the molecule allows you to implement an exponential dependence, an exponential increase in precision with the number of detected photons. This is why you won't be able to beat that, because exponential functions, of course, beat any other functions, and this is why I think this is probably hard to beat. I'm not sure. You should never say never, you know, and definitely I should not say that, but it's definitely hard to beat. Anyway, fields of view can be made larger just by scanning over large areas, so like in a confocal microscope, has advantages and disadvantages. An advantage is that if you implement it like in a confocal microscope, you have a single detector, you don't need a camera. Disadvantage is it can be slow because of course, the field of view scales, or the time it takes for taking an image scales with the field of view. The larger field of view, the more time it takes. And there is remedies like having many of these donuts working at the same time, and I think in the future something like that will come up. But for the moment now, the method is relatively slow when it comes to taking large pictures. It can be on the minutes, tens of minutes, or even hour scale if you take very, very large areas, but very, very precise. And the precision is shown here, it's below 1 nanometer. And again, these are nuclear pore complexes, or relatively early pictures that were taken with MINFLUX in my lab. And now these individual dots can be associated with individual molecules, individual fluorophores, and the precision is, as I said, of localization is of the order of a nanometer, of the size of the molecule itself. It's nice to compare it with STED, so it's about 10 times better than STED, very clear, and about 100 times better than confocal. I shouldn't compare it, but you know, I mean, I still like this comparison, although it's very obvious now. There's a factor of 100 in between them. And this used to be in the 90s, where both, again, I remember very well, the gold standard of resolution in a light focusing microscope. Anyway, for those of you who want to apply these things, there is something that I want to make abundantly clear. Please keep in mind that a fluorescent microscope, any fluorescent microscope, no matter which one it is, images only fluorophores, never proteins or other biomolecule, DNA. No way. Because the fluorescent microscope cannot see them. It's that simple. It can see only fluorophores. And this little sketch is shown here, this cartoon, to make it vividly clear to you what it entails actually for your practical work. Let's assume these are fluorophores, and this is a sketch of, say, a mitochondrion, so it's the inner membrane of mitochondrion. You will never ever see the crystal or whatever these things, structures are called. You always see just a fluorophore. So if you take a perfect picture, perfect picture with perfect resolution, molecular resolution, you will see only those fluorophores. It will look like this, It won't look better or anything else. You can't anticipate anything else because this is what the microscope can see. And of course, if they are separated by 5 nanometers, the resolution is 5 nanometers, no doubt, and you can separate them, of course. So meaning that high resolution, of course, means the resolution has always to be applied to the fluorophores, to nothing else, It's very clear that you cannot resolve anything better than that. Now you have to say, okay, if I want to see the crystal, I have to label more densely, clear, yes. Then you can maybe able to see those invaginations, but in essence, you won't see invaginations, you will see only the fluorophores that are actually shown in here, and you can envisage that, yes, there must be some invaginations of the inner membrane, but you see only fluorophores. So what I'm saying by this is that keep in mind you see only fluorophores. There has been a notion around which I must admit I dislike because they say, some people say that the resolution depends on the labeling density. That's not true. Resolution and labeling density have nothing to do with each other. The correct view of the whole thing is that you see just fluorophores and keep in mind that something that is not labeled, you cannot tell anything about it because you don't see it, So the good side about it, from my viewpoint, is that optical imaging no longer sets limits, very clear. So as it was in the past, that the wavelength limits the resolution or the lens and something, that's no longer the case, It's not the optics that sets the limits or the wavelengths. It is the labeling that sets limits for those of you who want to apply. So keep in mind that now it matters what the distance is between the fluorophore and the protein that you're actually interested in. And you cannot see that protein, of course, but and you have to infer from the fluorophore on the protein. But keep in mind, is that a valid assumption that you're making or a valid theory that you're coming up with? It very much depends on the effectiveness of labeling. Now, 10 years back, and definitely 20 years back, people would say, oh, come on, this is a luxury problem because, you know, these are small dimensions you're talking about, 3 nanometers or 4 nanometers. Yes, it's true. But now it has become an issue because the resolution is so good, yeah, that you see more actually of detail than actually what you can possibly infer. Now, with that, I have to make a disclaimer at this point, and many of you are aware I've co-founded with 7 or 8 of my former students 2 companies that specialize in super resolution, and they have commercialized this MINFLUX system. Tell you the anecdote, they didn't know that I'm developing this in my lab, so we developed it secretly for many years, and then at the time it was published in Science, I went to the company and said, I have a paper in Science today, and you should know about it. And they came and said, how does it work? And I explained them how it works. And of course, since I'm an employee of the Max Planck Society, I filed a patent with the Max Planck Society. And then they decided, I advised them, you have to take that license because this is going to be important. And they listened, of course, and they made it commercially available. And then as you've heard, one of the systems, one of the early systems is already here. And this has been taken actually now with this commercial system. So this is a 3-dimensional rendition of this protein called PSD95 in neurons, postsynaptic density protein. I don't want to bore you with this. So I'm just showing you, of course, it works not just in a, say, controlled environment as you can get in an optics lab, but it also works in a standard manner because it's a very robust concept. And not only can be used for imaging, it can also be used for tracking, like tracking individual proteins. And why is this tracking so interesting? Because it takes about 50 to 100 times fewer photons to get the same precision, meaning that you can track, say, 50 times faster. And then you can see molecular movements much faster in a shorter period of time than normal. And since I'm interested in pushing the boundaries in my lab in Heidelberg, in this case, we decided to go to the very limits and to minimize the photons even further and to maximize the speed because, yeah, I mean, this is what physicists like to do, go to the records, the next record. And so we developed a system that is slightly different from the first system we developed in my lab. It is also slightly different from the commercial system in the sense that it doesn't use a donut, but it uses a line-shaped 0 here in this case in the x direction, and then you can find out the position of a molecule in the y direction. And then we used sequentially 0 oriented in y, and that can be used to find out the position of the molecule in x. If you think about it as a physicist, using valleys rather than holes, donuts, has some advantages. They are not big, but they're subtle, maybe 20% more steep or something. And of course, if you want to push the limits, you don't want to compromise in any way. I'm not saying this is by far the better method. It has some advantages, has also some disadvantages because you have to do it sequentially x and y. But in any case, we have used this system in order to set up new records for localizing individual molecules. So here with on average 30 photons, you get a precision that is below 2 nanometers. And that's really good because it means that with just in very short period of time, within a millisecond, yeah, of a dye emitting, you have the precision that is substantially below 2 nanometers. So as a ballpark, so because it's easy to remember, 1 nanometer precision within 1 millisecond. Comparison with a camera, you need 300, 400 milliseconds to get to that precision. And that has allowed us to do tracking. And the reason why I'm showing you this is not because it was published 4 weeks ago in Science, but because I think this is opening a new field of application. And not being biologists well, then you go to systems that you track that are very well known and where the biology is not that complicated, and that is kinesin, because kinesin is basically in any textbook. It's even used in advanced lab courses when you study biology or so. So every biologist knows kinesin. And you probably know that that was done in the 90s and in 2004, 5, 6 by Paul Selvin, among others, Ron Vale, a co-discoverer of kinesin. They actually checked how kinesin works in microtubules. And you anticipate that it works in a kind of, call it hand over hand fashion or head over head fashion like this, from one dimer to the next, making 16 nanometer steps, and then the mid piece, the coil domain that carries the cargo usually moves about 8 nanometers. And so this is a very well-known system that was measured with the standard localization procedure with a camera by Paul Selvin and his people. And so we did that experiment basically and checked out how precise we can be in this case and how fast we can be. And so we got a very high precision per each step, and so below 1 nanometer, but the speed with which we could get that precision was 100 times, almost 100 times better than what they had with the camera at that time. And so because of the high precision at the same and the high speed, we could even see sub-steps here. And as I said, these are sub-steps here. You see 4 nanometer, 6 nanometers. And the precision of determining the size of the steps was very good, so below a nanometer. And that has allowed us to study those movements, to see how should I put it, if that step size varies or so under different conditions. And not only that, it also allowed us to do this under physiological concentration, because so the initial experiments done by Ron Vale and Paul Selvin, they had to reduce the ATP concentration by 2 orders of magnitude, because otherwise the kinesin is too fast. If you had constant ATP, then it moves too quickly, but we didn't have to do that. We could use normal ATP concentrations. Why? Because we're faster, and so we can see the movement in real time, so to speak. And so this has allowed us to do a number of experiments, including checking out whether this coil domain kind of rotates or not. What we did to find it out, we measured that the step size that is measured here in the coil domain. It looks like this. And then if you put 2 of them, this is a dimer, of course, and then you see the center of the 2, and then it is more centralized, and then you can infer from that that's obviously a kind of rotation taking place. These are subtleties just to show you that you can infer something new with this measurement. And as I said, initial experiments were done with 10 micromolar ATP, but we could go up to 1 millimolar ATP as a result of this fast detection capability, and could even find out or resolve a controversy in the field, in this kinesin field, which is actually the part of the step where the ATP is taken up. And we found that ATP is taken up when only one head is bound. And this was controversial, but I think now it's very clear. Not only that, it's possible to see rotations of these little, they call it heads. They should call them feet, but I don't know why they don't call it feet. But you can do that just by attaching a fluorophore at the end and then at the front of this little head or foot, and then measure the step sizes, and then you learn that there is a bias to the right and things like that. I don't want to bore you with the details of that. And as a matter of fact, I'm not a kinesin person. We just did that in order to prove that the method works, and you get high concentrations of ATP accommodated and this kind of thing. By coincidence, a group at EMBL worked on kinesin as well. I didn't know, so it was pure coincidence, or not coincidence. We had the same thought, I believe. And they used a commercial system. And the company didn't tell me that they had, of course, customers working on the same thing. Johan Sies, who was actually the lab head at EMBL in that group, approached me saying, "Oh, I've heard you work on kinesin. Why shouldn't we sort of publish together?" And then we agreed to put it on the same day on bioRxiv, because, you know, the first authors didn't want to not become first authors. This is quite the human side of it, and didn't want to mingle up the data. So it's okay. We tried to publish it back to back, and that's what we did. And so his paper came out on the same day. And the reason why I'm showing this, it's not just possible in my lab to do this kind of measurements, also with a commercial system. It's possible to do these measurements. To be fair, they can even do, with a commercial system, three-dimensional tracking. So that's not possible in our case because we have these line-shaped zeros, but they have a three-dimensionally shaped zero, which is an advantage. But the strength of the system in my lab is that it's slightly more precise. So we could see substeps of kinesin, and those have not been observed yet here in this system. May have also something to do with the biology, we don't know. But of course, there's always subtle differences. But in the end, this is just to show you that also in a commercial system, it's possible to take such dynamical movements with 50 times higher speed than what is normally possible. So what about STED that Sergei introduced at the beginning? Is that now completely outdated? And as said, that one of the merits of STED was that it opened up the field, and it was the first concept that used this on-off fluorophore transition to make a separation. I'm just repeating it. So you have excitation light, and you have the STED beam to turn the molecules off. Then you have the region where the molecules are still allowed to emit. And you can argue now maybe this is completely outdated. Now that we have MINFLUX, the answer is no, that's not true. Because STED, of course, can still be used for imaging, push button, get picture. This is, I think, one of the prerogatives of STED, in fact. But you can also, something. Was there a power outage?
Yeah, I think so. No, it's coming back.
It's dark over here as well. It also went off.
I don't understand. Yep.
Okay.
There we go.
Good, thanks. Yeah, and so in a way one can say that one can use this region actually of emission to kind of mimic a donut like this and look for the position of the molecule. So now there is no actual donut in the excitation light because it looks like this, but you can still kind of mimic it and make this region sharper and sharper and sharper. And in that way, you can localize molecules very, very precisely. From the viewpoint of this donut, it actually means that you're trying to get the molecule inside the zero without actually having the molecule face the large intensities of the excitation donut. So that's a big advantage. So there is no, so people initially, when they criticized that, they said, oh, but you will have large intensities on the molecule. This strategy basically means that this is always avoided, and the molecule is actually quite protected from leaching, as a matter of fact, and that's why this is a very, very effective method. So this is something that is basically has been developed in my lab in the last 2-3 years. It's not commercially available, by the way. And it has the advantage that the STED beam keeps the background low, which is also an advantage, and the intensity always sees low intensity. So the molecule sees low intensity. And so this has allowed us to really get down to small numbers in terms of precision, even smaller than we initially reported with MINFLUX. You know, development goes on. So with 1,000 photons, you're already down at 5 angstrom, and with 10,000, you get down to 2.3 angstrom. So localization precision becomes now insanely good. You can use this for imaging by having an on-off transition. In this case, it's done by a mechanism that the experts call paint, meaning that there's a binding by DNA hybridization of the fluorophore to the target of interest. And in this case, really you get down to say scale differences, distances that are of the order of the size of the molecule itself. So this is the size of the molecule itself. So to scale, to draw near to scale, 2 nanometer in diameter, 4 nanometer distance, and it means that you can still separate it. So, so this is also going to stay, I'm sure. I wouldn't say this is better than the other, because both have advantages and disadvantages, but it shows that this whole concept, yeah, of localizing individual molecules with a kind of donut pattern has fundamental advantages. As I said initially, exponential increase in precision and background suppression, getting to very high numbers, or small numbers, I should say, of precision. And here it's actually shown that you can easily even correlate it with electron microscopy. So this is an electron microscopy structure of this protein, NAP96, that nicely correlates actually with what we got with MinSTED, so in space. So the 2 data coincides actually quite nicely. And so you can come up, you can envisage for the future, and I think this will happen, a kind of interfacing between structure biology done with EM and fluorescence microscopy. Now, with this, I'm coming actually to the end. So the physics part, in my view, is rather solved. So the solution has been for fluorescence microscopy to tell molecules apart by on-off transition. And nothing else is the only, in my view, only valid explanation. And I haven't seen anyone coming up with a better one. So I've been saying this now for 15 years, and it may sound like a broken record, but still I haven't seen a better explanation. This is the only explanation. And of course, if you do the on-off transition on a single molecule level, then you have the smallest entity you work with, and then you have the ability to at least tell apart individual entities, molecules. But if you do it, the positioning with a donut pattern or with a 0, the resolution no longer depends on the wavelengths in the far field. So this is the new thing. So this is after 2014. So you're completely done. And then the practical limits, for those of you who don't care about the physics and the rest of it, yeah, the practical limits are now set by the chemistry of labeling and by the fluorophore size. And so a lot of effort has to go into this to make the labeling better. And I think the future will see a variety of very good labeling strategies and fluorophores and linkers and so on to make the power of the physical concept possible. Because right now the labeling strategy is lagging behind the physics. The chemistry kind of lags behind the physics at this point. So what can be done? Used for molecular maps, of course, of all kinds of things. Looking into molecular dynamics, I said movements, I envisage protein foldings, any conformational change. I think here MINFLUX really has an edge, because I do not know of any other method that can see small changes in position of a protein so quickly as MINFLUX can, non-invasively, even in the cell, as you've seen previously. And this is, I think, this is opening a new field. So if I were a very young biophysicist, which I'm not, of course, then I would go into this field, because there are so many things to discover, and the tool is there now, and people have not realized it yet. So it may still take 3, 4, 5 years if people fully realize what it means. But to me, this is very clear. And of course, drug discovery could be another area of application, and diagnostics and so on, you name it. And with that, of course, I'm coming to the end. I don't have large groups, you might be surprised. So these are actually people who have really contributed to this development. Some of them, like these 3, 4 people here, have left my lab already. 5 have left my lab. He also left. And these 3 actually are the ones that really are responsible for making the measurements and the experiments that were shown here as cutting-edge developments. Thank you very much.
thank you very much for extremely inspiring and interesting, and the talk is fascinating, physics and applications, and now it's open for questions. Yes.
Thank you very much, Stefan, for the very inspiring talk and for the high resolution of the images I can see. My question is about, so from your lecture, I can understand that the current the resolution it can be reached to the 1 nanometer, right? So do you think the size of the die, the floor, can also make a big difference on the resolution of the images? Because some of the die can be larger than 2 nanometers or 5 nanometers. So is that an issue for making make a smaller molecule of diodes to have a high resolution in the end?
Yeah. So the answer is yes, of course. Organic fluorophores have typically a diameter of about 1 to 2 nanometers, roughly. That's in the nature of the organic fluorophore. So if you look at bond lengths and this kind of thing, you will end up with that diameter if you want the dyes to emit visible light. That's very clear. The problem right now is not so much the length of the scale of the dye itself. It's actually the linker that links the dye to the protein or biomolecule of interest, and that is usually even longer. If you take, for example, antibodies, much too large, 10 nanometers or so. Yeah, that's much too large. Nanobodies, these are camelloid antibodies. They are 4 or 5 nanometers. So they're also very large, given what you can localize now. And then, of course, you can use say different labeling, like click chemistry-based labeling, which also got a Nobel very recently. So that could alleviate the problem to a large extent if it works. But then it will be the size of the die, basically. So there's one thing. So it won't get better than that. There is another aspect, which is finding out the position of the fluorophore. And that, as I said, can be scaled down to angstroms. And I'm sure there is also use for that. Because, if you know that something moves by 5 angstrom, yeah, that may reflect a real conformational change in a protein. So it's not so important to perhaps resolve 5 angstrom, yeah, because you have electron microscopy for that. But seeing a positional change of 5 angstrom, or a wobbling, or something, that may tell a different story for how an enzyme works, for example. You may be able to see the enzyme literally, how it makes its movements, yeah, because in the end, these are they are machines and they make this and that mechanically, yeah. And seeing those mechanical movements, I think, would be possible. That I'm 100% sure. And this method, in my view, is by far the best method. I do not know of any other that would be able to see in physiological context, in physiological environment, those changes and movements, say how enzyme makes this. Yeah. And I think this is a new field. This is why I'm saying if I was a younger person who wanted to go into something, yeah, probably I would do that because it's possible now to really see how proteins work, yeah, at their own scale. And the kinesin is just an example to show that we can access that scale of 1 nanometer within millisecond period of time. I think this will get even better. So this is not the end of it. So it could be maybe in 10 years, it is 1 nanometer per, say, 10 microseconds or so. Then you can perhaps directly watch the folding of proteins. You can directly see how it, yeah, folds. And then that's clearly something that can have a huge impact. Okay. That goes beyond imaging, far beyond imaging.
Yeah. Okay. You had your time for
Yes, I guess I did. So thanks a lot for a great talk. So I have 2 questions. One is, you were looking at this orientation and rotation of a molecule. Could you use the dipole, so polarization of the light, to get this information out? And could you also use this together, for example, as you're talking about protein conformational change, to get extra information out there?
Yeah, you can, of course, the majority of the work that was done here with the doughnut work is done with circularly polarized light. And the light that you have in your microscope, in your MINFLUX microscope, is of course circularly polarized for good reasons. The polarization in the line-shaped beam was linearly polarized to have a very good interference, a very good zero. And then, of course, you actually see if the molecule rotates, because then the excitation efficiency is different. If you and also if you put an analyzer, a polarizer, into the detection plane, then you would see, of course, that the emission slightly changes its polarization. So these experiments are possible, especially on a single molecule level. There's no doubt about it. And one could also combine it with lifetime, sure. And then you get even more out of it. You can perhaps even get a scale on which this time scale on which this happens, and in a sub millisecond domain. So these are all experiments that you could do on a single molecule level. And of course, you can also think about MINFLUX replacing or not replacing or complementing, whatever, to how to formulate that in a polite way, FRET. Because FRET is all about seeing interactions between two molecules, yeah, fluorescent molecules, in order to assess proximity of proteins or so. And I think MINFLUX has the precision now to really measure distances between molecules without the uncertainties that are related to the FRET process. And there are substantial uncertainties connected with making FRET measurements. And so these are immediate things that can be done, even with a commercial system.
Yes. Thank you. And then my one question, you said basically the physics is done. So what are you going to be doing now?
Yeah, that's a good question, Jonathan. I'm asking myself. Yeah, I'm thinking about it too. Yeah.
Okay.
Thank you for your great talk. I'm a medical doctor, so this is a medical doctor question. Is the human eye a limitation? And one question that came into mind was that there seems to be differences in male and female visual acuity. And I'm just looking at your students up here and thinking that maybe males have higher visual acuity. Do males see more detailed in a microscopy?
It's a philosophical question. I think you, as a medical doctor, are perhaps better capable of answering the question. But on a serious note, the eye visual perception doesn't play a role anymore because everything is done electronically. So in the end, you don't look into a microscope as you would do, say, in Abbe's time or Rayleigh's time. You just get it on the picture. Yeah, so none of our images are actually images that you would instantly see. So it's all reconstructed on a computer screen. Why are there fewer women than men here? When I studied physics in Heidelberg, we started out with about 120 people. 3 of them were women. This is the plain fact. And of course, it improved. So there are by far more women, and also in my lab, by far more women. Actually, I have now in Göttingen, I have 4 PhD students, 3 of them are women. Coincidence, I think, because there are more applying. Yeah. Other than that, I don't have an explanation. I think it's an interesting subject. I think it's just my personal gut feeling. There is no how should I put it? There is no reason why women and men wouldn't perform equally in sorting out a certain project. But there is a tendency of men to go more towards technical thing. This is also a fact, and as scientists we have to acknowledge this fact. This is a plain fact.
Why didn't you choose not to choose to go to humans? Why didn't you choose not to go to humans?
Yeah. It's yeah.
last question over there.
Hi, thank you for the interesting talk. And my question is, can you explain more about the Z localization and preciseness? How can you, like, in terms of
The
optical
Z
physics?
localization.
Yeah.
Yeah.
How can you increase the preciseness of Z localization?
The Z localization, so in the MINFLUX case and also in this commercial case, the hole is not just a two-dimensional hole, it's a three-dimensional hole, so there's light above and below the hole, and that's why you get a 3D. And this is why this tracking of the EMBL experiments was three-dimensional. So in my experiments, I never concentrated on Z because being a physicist, I said, okay, what you can do in X, Y, you can also do in Z. And I wanted to push the limits. I wanted to understand the basics of it. But it's not that one couldn't do things in Z. You can do it in Z. Sometimes better, sometimes worse than in X and Y, depending on what you do. For STED imaging, Z is usually not as good as X and Y. MINFLUX imaging or MINFLUX localization, X, Y, and Z can be quite equivalent. Or even slightly better in Z.
We have to stop now. So
Okay.
let's thank Stefan Hell again.
Thank you.